All right, so we're going to go ahead and review how wind forms on planet Earth because our big question is, well, what makes wind happen and how does Earth's rotation affect global wind patterns? So please recall the demonstration where we had some marshmallows in a plastic bottle and I added some extra air molecules or added some extra air pressure to the bottle by using this little carbonator thing, this carbonator pump that pumps air into it. So you can see how low the level is of marshmallows, and they sound pretty hard. And you can look at very closely and see that they're like super wrinkly. Look at those little guys. They're very wrinkly. All right, so let's see what happens when I remove the tape. Remember, there's a hole down here. Let's listen carefully and see if we can see what happens when I take the tape off. Whoa. Ooh, that smells good. Smells like marshmallows. I just made some marshmallow wind. And take a look at the marshmallows. They don't sound like they did before. They're back to a nice thud, and take a look at them. They're not all wrinkly. They're nice and billowy, and look at that. They pretty much filled up back to the black line. So when I released the air molecules, they escaped really fast out this hole, and they were moving from an area of high pressure to an area of low pressure outside of the bottle. So let's go ahead and note that on our graphic organizer. That was what we observed. Right up here. Oh, don't forget to put your superhero name up there and whatever class period it is. This should be glued into your notebook. So, draw how air molecules behave. When pressure is added to air molecules, well, let's draw a picture of it. We're going to draw our little bottle over here, and we're going to draw that the bottle has a lot of air molecules in it, like tons. They are packed in there, packed. Lots of air molecules. And the air pressure is super high because they are pushing against the side, and they're just really highly packed in there because I added a whole bunch of extra in there. So let's go ahead and draw in a whole bunch of packed molecules. And we're going to go ahead and say high, right? High pressure. And it says it right below. This is our high pressure bottle that we've added tons of air molecules to. It's packed in there. All right. And then let's go ahead and add the hole. Here's our hole. So wind blows from high to low, because out in the outside of that bottle, there's low pressure. There's not a whole lot of air molecules all packed in one place, all pushing on the walls and things like that. So let's just draw a few little air molecules out here. This is low pressure. They're not all in there squeezed in together. So we're going to go ahead and indicate that wind is blowing from high pressure to low pressure area. This is what makes wind happen. All right. We also made some observations of what happens when the Earth rotates. Over on this side, we're going to go ahead and write what we noticed when the Earth was not rotated. So remember, I had that little globe. I dropped the green wind blob onto it. And what did it do? It just went straight. So we can say we noticed a straight line of wind. Right? And then we had the balloon spinning, and we noticed that it made a curvy line. And we'll go ahead and draw that on, that it went like that when the wind was spinning. This is what we call the Coriolis effect. Coriolis effect. Coriolis effect. Which balloon was more like the Earth? Based on what you observed, draw what you think the wind patterns on Earth might look like on the Earth below. So when it says balloon, globe, either or. All right, so down here, we're going to go ahead and draw what we think the Earth spinning does to the wind patterns. And it really does help if you go to page 277. There's a really great model of the different zones that happen on the different belts of Earth. So let's go ahead and draw in a few little lines, latitude lines. So these are lines of latitude. They're like different belts that go around the Earth. It's like we've got a smaller belt, a bigger belt, and then the biggest belt that goes around the equator, around the center of the Earth. And we're going to go ahead and draw in some global wind patterns. Wait, so we've got 1, 2, 3, 1, 2, 3. Yeah, okay, so this is 0 degrees right here. So we're just going to draw in some wind curving. The wind is curving. Let's go ahead and draw that wind curving. And if you're spicy and you want to know more about the curvation of the wind, you can go ahead and read page 277, which discusses global wind patterns. Let's go ahead and review what drives this entire process of everything happening. Oops, oh man, you couldn't see any of that. Sorry, Miss Shallon can't see the thing. Oh, man. All right, well, you can go ahead and pause it so you can see what that looks like. Let's review what happens when we add thermal energy to air molecules. What do? Do they slow down or do they speed up? That's right, they move faster. And they move farther apart. They spread out. Okay, so let's draw some molecules spreading out as they heat up. Okay, now we're going to put all the pieces together. Let's go ahead and open up the graphic organizer. We're going to start at the beginning. What drives this entire process? We're going to start over here with number 1. Solar radiation. Thermal energy from the sun reaches Earth, heating land and water. So let's go ahead and draw a sun here. This is our sun in this picture. We're going to illustrate this entire process. That means we're going to draw a picture of the entire process of how wind happens on planet Earth. Illustrate the words near each description. So each description, we're going to draw what we are reading. Okay, we're going to draw a picture. And then I'd like you to color it at the end as well, please. So, number 2. Oh, wait a second. Let's make, since it says it reaches the Earth, heating the land and the water, let's make some thermal energy going all the way down to the Earth. Let's go ahead and make a ground. We're going to make some ground down here. Hang on. Zoom it in, zoom it out a little bit. So here's our land, right? And then I'm also going to add some water on this side because it says land and water. We're going to draw some thermal energy getting down to the Earth, some heat getting from the sun to the Earth, heating up the Earth. So let's go ahead and indicate that the Earth is heating up and there's some heat happening because the land heats, right? So let's draw some little heat arrows. And it says, air above the land and water heats up. Air molecules move faster and farther apart. Air becomes less dense. That means it's less heavy, and it begins to rise, creating a low pressure zone below it. So let's go ahead and indicate that these air molecules are heating up, and they are rising because they're becoming less dense. They're not as heavy, so they're not sinking and down below anymore. Let me zoom it in a bit. They are rising. And let's go ahead and say that this is what we call a low pressure zone. Low. We're going to label that as low. Low pressure. There's not a whole lot of pressure because there's not a whole lot of air molecules pushing down, causing pushing and pressure. There's not very much, right? This is a low pressure zone. So let's go ahead and just say warm, less dense air rises. Okay, so we've got our air rising. Now let's move on up to number 3. it says cold upper atmosphere. So way up high, it's very, very cold. Air molecules cool and condense. Cooler air from higher in the atmosphere is heavier and it sinks. So we're going to go ahead and make some air sinking. Let's go ahead and draw what we just read. We're going to draw a picture of what we just read. We're going to draw some air molecules cooling and condensing. So we should remember that when molecules condense, they come together. They come closer together and they pack in there. Lots of them packed in. So let's go ahead and draw some packed in molecules packing in and being very dense. So this blob of air over here is more dense than this blob of air over here, because this one only has a few molecules and this one has dense molecules, lots of molecules. So we're going to go ahead and say cold, dense air sinks. Because now that it's so dense and there's so many of them, it's heavier. Denser things are heavier. And when stuff is heavy, it sinks. So if we're in the water and we put something heavy in the water, like a bowling ball, it is going to sink compared to putting a basketball in the water, because the bowling ball is more dense. Its molecules and atoms are all packed in there compared to the basketball that's full of air molecules that are less dense. So let's go ahead and draw some arrows indicating that this mass of cold, dense air is now sinking. So as the air pushes down, it's applying pressure on everything that's below it. So that's what we call a high pressure zone, when this dense cold air is sinking down. So let's go ahead and we're going to label this HI for high. And we're going to say high pressure zone. Please label that high pressure zone. And number 4, the final step. Cold air is sucked into the low pressure zone to replace the rising warm air. This is wind. So as this low pressure, we forgot to label pressure zone. Let's say pressure zone. As this warm, less dense air is like floating up, there's sort of like a hole, and it sucks in this cold, dense air that's like sinking. And so we're going to show that the air is now moving. It's getting sucked into this low pressure zone. So we've got high pressure zone over here where the air is cold and dense and sinking. It's getting sucked into this area. And that sucking of air over into the low pressure zone is what we call wind. So we're going to say wind blows from high to low. Wind blows from high to low, in that direction. All right, please go ahead and color this picture in, make it nice and beautiful. And that is our review of how wind is formed.